This evening I'd like to tell you a little bit about my research in thermonuclear fusion research. And in particular, I'd like to tell you about a hero of mine who is this chap, Edward Murphy. Now, Murphy is often attributed the law that states that anything that can go wrong will go wrong. And this is often used to describe the cussedness of nature, the fact that anything you try to do will be overcome because you're battling against the very nature of things and their tendency to go wrong. But it's actually Murphy who came up with this idea originally to not describe how cussed things were, but how we should all anticipate what can possibly go wrong and try to design around it. So Murphy was an engineer working on a project to do with rapid deceleration of human subjects. In fact, he worked with John Paul Stapp on the rapid deceleration in a rocket sled. And it was an engineer who put the decelerometers onto the subject, who put them all at 90 degrees to the direction that they were supposed to be. So he described this engineer as if there was anything that could be done wrong, he would do it the wrong way. But he actually saw this as a way of doing defensive design, to try to anticipate the worst case scenario in any engineering project. And so, as you'll see, hopefully in this lecture, fusion is strewn with many of nature's pitfalls, which we have to try to circumvent and get around and design improvements to the system to try to overcome them. And it's my belief that actually, if we are capable of doing that, we can actually get nuclear fusion to work. Now, you'll often hear fusion described in terms of a potential source of the energy crisis. In order to illustrate that, I'd like to introduce you to a very particular and special liquid. Now, I have a little bit of it here, and I have to be very careful with it because it contains about 300 times as much energy per volume as petrol. Cheers. Because if you look inside any glass of water, one molecule in 6,000 will not contain a hydrogen atom, but will contain a deuterium atom. And deuterium is something which is a heavy variant of the hydrogen atom, which can be forced to undergo a nuclear reaction, a fusion reaction. Now, it's the same fusion reaction that is at work in the sun, where we're fusing hydrogen. And so, to my mind, the solution to the energy crisis does not lie necessarily with the fossil fuel inside the tanker, but inside the water which it displaces. The water displaced by the tanker actually contains many times more energy content than the fossil fuel itself. All we need to do is replicate the fusion process of the sun in order to try to generate that in the laboratory. Now, that's, of course, easier said than done. But the way in which we typically try to do this is using two different forms of hydrogen. So we normally think of the hydrogen as a proton in the nucleus surrounded by an electron. But it has a heavy variant. It's heavy because it has an additional neutron, and that's deuterium. There's also a third variant of hydrogen which has two neutrons. And if we can force these two particles to come close enough together, they will react with one another. The strong nuclear force will reorientate their structure, and we'll end up with a helium nucleus and a spare leftover neutron. Now, you might think if I just throw these two particles together, then I'll get a reaction. But of course, both of these particles, tritium and the deuterium nucleus, are positively charged. So if I do that at low speeds, they're just going to repel one another. In order to get them to within a close enough distance to react, that's about a millionth of a millimeter, I need to have an awful lot of energy in order to overcome this repulsion. And that requires a velocity something in excess of 1,000,000 miles an hour, at which point I'll get a reaction and the two will split together and form a helium nucleus and a neutron. Now, it transpires that the reordering of these particles by the strong nuclear force from this configuration to this configuration changes their mass just a tiny amount. So what you end up with weighs ever so slightly less than what you started with. And that deficit of mass, that change in the mass of the system, can be released in the form of energy, according to Einstein's famous relation E equals mc squared. That energy normally comes off in the kinetic energy of the high-speed neutron flying off from the reaction. But each one of these reactions is only going to produce about a millionth of a joule of energy. So doing it one at a time is very ineffective. So instead, what we typically do is we take a material of fuel and we heat it up to a temperature of about 100 million degrees centigrade, at which point it becomes a plasma, and that's basically where the electrons and the nuclei have separated and are moving separately inside the fluid. If I can move all of the particles around at high speed because they have enormous temperature, then some of them will undergo a reaction. Not all of them, but some of them. And so the trick now becomes being able to hold something at 100 million degrees for long enough and at high enough density in order to extract a decent amount of energy. And there are two basic approaches that are undertaken by almost all nuclear fusion experiments. The first is a quite elegant system that involves wrapping the outside of this plasma with magnetic fields. So this pink region here, which is donut-shaped, is the plasma, which is filled with deuterium and tritium ions. And on the surface, you'll see a whole series of magnetic fields. This is what's called a tokamak arrangement. Now, when this was first tried back in the 1950s, it was done in a plasma of a few meters in size. And the initial results suggested that actually we may be able to confine plasma inside this magnetic bottle for long enough to get some fusion reactions. But charged particles of the plasma don't want to cross across this magnetic field line, and so they're confined within. But it soon became apparent that even though we're trying to confine the plasma with this magnetic field, eventually the plasma ions will collide together, and they'll knock each other from one magnetic field line to another and gradually diffuse out of the system. And the only real solution to this was simply to make the plasma vessel bigger. So in the 1980s, the Joint European Torus was constructed in Oxfordshire. This is now the largest tokamak plasma in the world. And even this isn't large enough to be able to sustain or confine the plasma for long enough to get energy. And so under construction now in the south of France is ITER, which is several times the size of JET. But that won't be ready for another 10 years. Now, the other approach to trying to confine the plasma, well, that's a bit of a misnomer, really. We're not really trying to confine the plasma at all. This is a very belt and braces approach. The idea is to dump so much energy into the plasma so rapidly that will compress it to a very dense state. And when it's very dense, it reacts very quickly. The idea is actually to get it to undergo reactions even before it's had a chance to explode. So this is normally done by taking an intense source of radiation, maybe particles or laser light or X-rays, and bombarding the surface of our fuel until the surface explodes off very rapidly, and as a recoil to that surface expansion, the interior starts to implode and becomes very dense, very hot, very quickly. So this requires two things. It requires an extreme state of matter that we call high energy density plasma, where the pressure inside can be several 100 billion times the pressure of the atmosphere. It also requires that we deposit a huge amount of energy onto this fuel in a very brief period of time, something like 1 million joules delivered in a few billionths of a second. And this number is 500 terawatts, but to give you some reference, 10 terawatts is what you would get if you took all the power stations in the world and added together. So this requires 50 times that power level. Now again, this was originally conceived as something that would require something like a 10,000 joule laser. So you see a room full of laser here, a person for comparison size. This was thought to be enough to get this to work. But again, it rapidly became clear that if we can't survive the sorts of laser intensities, we have to dial those down, and we can't implode at an arbitrarily high velocity, we have to dial that down too. And both of those require going to a higher energy. And so this was the system in the 90s as an overlaser. And now, just recently, in the last couple of years, the National Ignition Facility was built to try to achieve this. And this is a monstrously large facility, as we'll come on to later, but it has over 2 million joules of energy. And the idea here is rather than to hit the capsule with the laser light, the lasers bombard a little cylinder surrounding the capsule, and X-rays are then generated, which compress the fuel. Now, fusion is often a great motivator for students wanting to study physics, and the same was true in my case. When I first came to Imperial College in 1987, I was met by Professor Malcolm Haines, who offered me a PhD position. Now, as Joe said, Malcolm is known to many of the people in the audience, but for those of you who don't know him, he was a true father figure to plasma physics in the UK and in the US in particular. He was a great mentor to me, and much of the work that you're going to see this evening was due to his inspiration. So when I came to Malcolm, he suggested to me that I might like to think about an alternative way of achieving fusion. And those of you who know me well, in fact, those of you who probably just met me, may realize that I'm not necessarily the most patient of individuals. And so the idea of waiting 20 years for a fusion reactor to work on a tokamak wasn't terribly appealing. And I think Malcolm saw this, and he recommended to me that we work on a slightly higher risk idea for fusion, but one that could potentially bear fruit quicker. And this was actually reusing an old idea of trying to confine the high temperature plasma. You have a huge pressure inside the plasma here, but we also pass a very large current through that plasma, and that produces a magnetic force that balances the pressure. What was new about this was the idea of trying to use this in very dense initial targets. So we froze hydrogen to about minus 260 degrees, at which point it becomes like toothpaste, and you extrude a little fiber of that and then try to pass a very large current through it. Now, as I said before, the name of the game with these things is to try to put as much energy in as possible over the shortest possible time. We were very fortunate that Malcolm, shortly after I finished my PhD, managed to secure a relatively large amount of funding to build this, which is the Magpie Generator, which sits about 100 feet that way. Now, this is a capacitor bank that is used to generate large compression of power. To illustrate that, what I've got here is another capacitor bank. It's called a Marx capacitor bank configuration. These blue squares, which I'm not going to touch, are capacitors, and I'm going to charge each one of them up to 10,000 volts. But you'll see in between each pair is a little screw head, and that acts as a little switch. When I trigger those switches, they'll form a little blue flash, which is a conduction channel, and that will take the capacitors from a series configuration to from a parallel to a series configuration. We'll add all the voltages together and hopefully get about 120,000 volts on the output. Now, I'm just going to turn the lights off to help you see this. And if I hold down the button, there you go. So what you're seeing are breakdowns between all of the pairs of screws between the capacitors, and they're adding the voltages together. On the right-hand side, from my point of view, is one large spark which takes that down to ground. What we've done there is produce a flash of light that lasts just a few millionths of a second, but in doing so, we're taking a few watts of electricity from the power supply and compressing it down in time so that we get several million watts in the final spark. So imagine what would happen if instead of capacitors of that size, I have capacitors of this size. So this is a Magpie capacitor. It weighs about 100 kilograms, and you'll notice inside the Magpie design here we have 96 of them. So Magpie is able to produce a very intense electrical pulse, and it was that we wanted to apply to the fiber. Now, when I finished my PhD in 1990, we were just beginning to build Magpie. And so rather than spend the next 3 years in front of a computer, I was given the option of hitting large lumps of steel with hammers, which I call pulse power engineering for the next 3 years. So you'll see a little exhibition of my style of pulse power engineering. It's me in the green shirt here, and what we're trying to do is lift the last stage of our transmission line that weighs about half a ton. You'll see a liberal application of a 6-foot crowbar to the crane system at this point, which finally allowed us to get the thing into place. Now, after we finished building the Magpie generator, I was one of several experimentalists working on this idea of trying to compress hydrogen fibers. I only put this picture in really to convince my children that I did actually look youthful and slightly thinner at one stage in my life. But you'll see here that I'm manipulating a set of X-ray diodes on top of the Magpie chamber. Now, picture the situation. It's late at night on a Friday evening, about 7:30. At the time, we were using superglue to mount the targets inside the vacuum chamber. So I crawled on top of the machine, put the target in the chamber, inadvertently knocking over the bottle of superglue as I went, and placing my hand in it to steady myself. As I tried to get away from the center of the chamber, I noticed that my hand wasn't moving. Now, I don't know if any of you have ever glued yourself to a terawatt pulse power machine before, but Magpie weighs about 150 tons, so the idea of taking it home with me wasn't a starter. So after crying out, hello, can anyone hear me, for a little while, I managed to prise myself free with a metal ruler. Now, shortly after this, I had something of an epiphany, which was that maybe I wasn't really cut out for experimental work. The other thing that convinced me of that was the results that we were getting from those hydrogen fibers. So these are images of the current at different times. You see that the confinement of the plasma by the magnetic field has gone sadly wrong. And the reason for this was actually a well-known instability associated with plasmas, where if I have a variation in the surface thickness on the plasma here, I get a slightly larger magnetic field here than I do up here. And this neck region is compressed by the magnetic field. This bulge region is systematically just has lower and lower confinement. And so that's what's going on here. Hopefully this is a numerical simulation that shows the current initially flowing in a plasma on the outside of our fiber and the loss of confinement in some regions and confinement only in others. Now, when this was going on, there was another program under development at a larger pulse power laboratory in the States, Sandia National Laboratory. And we started looking at this in interest as potentially a way to get around the problem with our starting with a dense plasma. Here the idea is, instead of starting with something dense and just blowing it up, you start with something not very dense, something big, and try and implode it to make something dense. And that's done essentially by taking a large number of very thin metallic wires. These are tungsten wires, a few microns across, and Dolores here is assembling them into a cylinder about 1 centimeter in radius. And the idea is that the magnetic pressure, or the magnetic force applied to this, is going to cause the thing to implode very rapidly. So on these experiments, that was done using this machine, which is the big brother of Magpie. It's about 10 times the size and 100 feet across. And this is called the ZGenerator, very enigmatically, at Sandia National Laboratory. It produces today about 24 million amps of current. The idea here is to try and make a cylinder of plasma as thin and light as possible, and then by passing this enormous current through it at a massive force on the outside, to get that to implode, again, at a few million miles per hour. And this is a way of converting the magnetic energy of the generator into the kinetic energy of the object, and then into heat and radiation as it compresses into the middle. So imagine, if you like, something that weighs about the same as a flea and has the same kinetic energy as a speeding motorbike. Something like this. Right. Now, we thought it very interesting to try to explore how these objects were working. So we were very fortunate at this time that we had both an experimental campaign led by Sergei Lebedev and a computational campaign that I was developing a new computer code in order to model experiments on Magpie that looked at wire arrays. So there were many competing theories at the time about how wire arrays work. But basically what happens is, if I pass a current through these little wires here, they turn into plasma quite slowly. And some of that plasma you can see bleeding away from the wires here is then accelerated down towards the middle prematurely and gives rise to the formation of this dense column of plasma. You can see it here in X-ray emission from a bunch of wires here, streaming plasma towards the center here. Then eventually the wires will start to run out of material, and so they start to break apart. And as they do so, you get all of these magnetically accelerated bubbles that then converge towards the axis and crunch together. And that's the time at which we get this very bright pulse of X-ray out. Now, my particular interest was to try to use these in fusion research. And that involved modeling some of the experiments happening at Sandia National Laboratory that had much larger wire arrays and required much larger calculations in order to simulate them. So here again, you have a wire array. We're looking at it from the side. And in fact, there are two cylinders of wires here. One goes from this position to this position, so all of these bunch of wires here. There's another called a nested inner cylinder here. And this is a very large calculation run on a big computer at AWE. And what you see is as we try to sweep all that material in towards the middle, it does so in a highly irregular way, and it doesn't all arrive on the axis simultaneously in a nice controlled manner. So you see the wires evaporating, they break apart, and as they fly in, we've actually put this in a bunch of wires here to try and catch and decelerate some of it, and then it all turns into a non-uniform turbulent system on the axis. This, despite its non-uniformity, represents still one of the world's most powerful X-ray sources. Dissipating all that kinetic energy in a few billionths of a second produces several hundred terawatts of X-ray. Now, one of the big problems we had was convincing people that these were truly three-dimensional objects. And the reason for this was that historically, most people, when looking at a wire array like this, had assumed that the wires would instantly turn to plasma and that we had essentially just had an imploding cylinder. So rather than go to the trouble of modeling the entire volume, we would instead just model something that was two-dimensional in state. So this is the height of the system and this is the radius. So these are comparisons done by Chris Jennings of this 2D approach with the 3D approach, which you can see produces much more structure at the stagnation point when it crunches in the middle. So the problem here is that I have an axis of symmetry in this problem, which means that anything that comes this way is met by an equal and opposite object moving the other way. And that means that everything has to come to a dead stop when it reaches the middle. When you model the entire volume like this, things don't come to a dead stop. They tend to pass through the middle from one side to the other. Now, this seems like a minor modification, but it's only by doing this that you actually get the answer right. And so we've spent many years trying to persuade our colleagues that they have to invest the effort required to model the full volume of the system. And so here we see, for example, this is a comparison of emission images. So this is the X-rays coming out of one of these objects on Magpie, and these are a time sequence of simulation results. We can only get this right if we model all of the plasma. So to model the whole system is actually quite a complex problem, because if we look at how we model plasmas, there are many competing effects that we need to take into account simultaneously. So cooking up a plasma model can be done by taking elements from different parts of physics. So for example, I need some hydrodynamics because I need to model how the fluid flow moves around. So I'll take the Navier-Stokes equation from fluid dynamics and put that in the pot. I'm also going to accelerate everything with electromagnetic fields due to the current. So I'm going to take Maxwell's equations and put them in as well. But the main thing I'm interested in doing is heating and compressing the plasma. So I'll put in some thermodynamics, a heat or energy conservation equation. And the dominant source of energy inside the system in these imploding plasmas is, of course, X-rays, because that's one of the main products. So those X-rays can be generated in one part of the plasma and be reabsorbed elsewhere. So I need to model how that energy flow happens with X-rays. So I take a radiation transport equation for that. I might be interested in knowing the details of the spectrum that comes out from this X-ray source. So I'll put in some atomic and spectroscopy physics. And then finally, of course, the real thing I'm interested in is fusion. And so I have to calculate the nuclear reaction rates and see what that produces. And so we put all that in the pot together and we mix them together to make a plasma model. And if your cooking's anything like mine, what you end up with is something pretty hideous. But the point is that none of these effects on their own are particularly new or challenging physics. What makes plasmas particularly challenging is the combination of effects and the way they play off each other and feedback on one another, and that's what gives rise to complexity in the plasma solution. Now, if I try to represent something like this on a computer, it's not just a question of solving those equations once. I have to try to look at detailed structure of the imploding plasma, something like this. So if I zoom in on this computer representation, you'll see that the way I've represented it is by a series of tiny little cubes. And what I have to do is solve the rate of fluid flow or magnetic field flow or X-ray flow between each one of the cubes in this system in order to solve those equations. But not just once, of course. I have to then solve as a function of time at several times throughout the system to see how it evolves and collapses and moves about. So if I were to do that on a single computer, I have roughly 100 million little zones of space, or computational cells as we call them, in this calculation. If I were to do that on one computer, it would sit there getting very hot and wouldn't get anywhere. So the idea is that I can divide this problem up spatially into a number of different separate domains, each one of which has only a few million computational cells within it, and hand each one of these domains over to a separate computer. So the way we do this is in what's called parallel computing, high-performance computing. It literally equates to giving part of the problem to this computer and then getting it to communicate its results with its neighbors. Now, if I were to build a parallel computer, I'd need several hundred processors or even 1,000 processors out of separate boxes like this. It would get very large. So instead, what we use is very small-scale, tiny computers which are stacked together inside a 19-inch rack. And this is a picture from the CX1 and CX2 high-performance computing clusters here at Imperial College. Now, of course, you generate an enormous amount of heat from all of those computers in close proximity, and so we have to deal with that heat. And it's an interesting coincidence that a 19-inch rack is roughly the same size and shape as a coffin. So it's actually a convenient way to cool a 19-inch rack down is to use the same cooling technology as is used in a morgue in order to cool the coffins. So strapped to the back of these 19-inch racks are a set of coffin coolers. Now, if you ever walk into CX1, you'll see a huge amount of heat being generated, a huge amount of noise being generated from several thousand processors and all of these coffin coolers, and it kind of makes you feel that you've walked into a different world. Okay? So now the real reason for being interested in these wire arrays, as I said, was motivated by fusion. And the way this was approached at Sandia Laboratory was something like this. We would take our little fusion fuel in a spherical ball here, and we want to bombard that with a lot of X-ray heat in order to drive it to compress. We can do that, for example, by having a wire array Z-pinch up here and another one down here. And if I pass a current through those wires, you'll see that they vaporize, and then they start to accelerate, and then they implode. And as they do so, they crunch together in the middle, generate a lot of X-rays, and the X-rays then are fed through into this cavity down here, and that drives the capsule to implode. Now, Sandia were able to get very good data from radiography. This is taking a snapshot of the imploding capsule on a system like this. But one of the problems with this is that whilst these objects are extremely efficient at generating X-rays, you have to then take the X-rays out from this region here, couple it through a small hole, and feed it onto the capsule down here. And that coupling process was relatively inefficient, which meant that Sandia weren't able to compress these capsules enough to get a significant amount of fusion from them. The other thing that caused that problem to grind to a halt, that program to grind to a halt, was that at the same time, the US Department of Energy was building this, which is the National Ignition Facility, pretty much to do the same job. Now, NIF is an enormous and very impressive project. It's about 6 football fields in length, and each one of these pipes running down here is one of 192 separate laser beams. Each one is as large as any other laser beam that was previously built. All of that energy in laser light is designed to be fed into a target chamber here and fed onto a tiny little pellet of fusion fuel in order to get it to implode. So if we look at the target area here, this is what it looks like. Well, actually, this is a slide from the latest Star Trek movie, but you may be interested to know that in this latest Star Trek movie, the part of the engineering deck of the Enterprise was played by the National Ignition Facility. So they rented out the National Ignition Facility for several weeks, and what you see here are the beam lines and the diagnostic ports, which are all pointing radially inwards. This is the wall of the vacuum chamber, and the vacuum chamber is about the size of this room. Embedded within that is this tiny microscopic pellet, about 2 millimeters across. And the idea is to generate X-rays, which then bombard the surface of this and cause it to implode in a few billionths of a second and get to the pressures required. So what we have here in this representation, this yellow region here, is made of plastic. The green region here is ice made out of the deuterium and tritium. So this is cooled to about minus 260 Kelvin, and the fuel is frozen onto the inner wall of the ball, and there's a little bit of gas inside. Now, if I expose this to the radiation from all of the X-rays, you see the first thing that happens is the surface expands and blows off. And as Newton's third law says, if anything's going this way, then there's a recoil force which forces it to come in this way. So that shocks up and accelerates the fuel and compresses it spherically, and then something magical happens at the end. Now, this design has always struck me a little bit like the physicist who, when asked to design a new racehorse, comes up with a spherical horse moving in a vacuum. It is required to be perfectly spherical and symmetric in order to work. But if we look in a little bit more detail about the environment that that capsule sits in, there are very many reasons why perfect spherical symmetry might not be achieved. For example, the capsule is embedded within this cylindrical tube called a hull ram, which is made of gold. It's held in place to stop it falling down with these little plastic envelopes. And in addition, you probably can't see it from the back of the room, but there's this tiny little tube here which is used to get the fuel into the inside of the capsule itself. So the departures from spherical symmetry. The other thing that's going on, of course, is that the lasers are generating X-rays on the inner surface of this gold wall, and the X-rays are then hitting the capsule. But if I look at the uniformity of the X-ray emission bombarding the surface of the capsule, it's not perfectly symmetric. And of course, it will be less symmetric if I don't get every laser lined up perfectly. Finally, the scientists at Lawrence Livermore Laboratory gone to extraordinary lengths to make the spherical surface, or the outer surface, as perfectly smooth as possible. And these are a triumph of engineering with the surface roughness that they have. But they still have a finite series of defects on the surface. Here I've had to amplify them 100-fold so that you can see them. But nevertheless, these defects can have a major imprint upon what goes on in the implosion. Now, the reason for this comes about from one of nature's other tricks that she likes to play on us, called the Rayleigh-Taylor instability. And the Rayleigh-Taylor instability essentially sets an ultimate speed limit for the universe. If you try to implode the capsule beyond about 300 kilometers per second, so that's about 600,000 miles an hour, the capsule will actually disintegrate. Now, the reason for that is very much the same as what happens if I try to tip a glass of water upside down. So here I've got a glass of water. I'm going to try and tip it upside down and keep the water inside the glass. I'm going to do this by simply putting a piece of paper on the top of the glass like that. Now, please don't do this when we get upstairs with the wine. But you may think that the paper is just holding the water in the glass, but it's not strong enough to be able to do that. Of course, if the water tries to just move down as one bulk, you would have to set up a vacuum behind it to hold it in place. So the reason water normally falls out of a glass is the interface between the water and the air underneath isn't perfectly flat. And a little ripple in that surface will allow some of the air to start rising up and some of the water to start falling down. I can stabilize that system if I make the surface between them perfectly flat. Now, if I perturb that system from perfectly flat, it has inevitable consequences. So imagine what happens if I take the defects that we think we see in the system, and then I try to accelerate them to implode. So what I've done here is the same kind of calculation. This is the plastic, and you see I've put a series of defects, about 13,000 separate defects in the surface of the plastic here. This horrible purple color here represents the surface of the fuel. So if I do the same thing, I bombard this system with X-rays and I blow the surface off, you see some of those defects start to get compressed and they appear to have disappeared by this point. But as the thing accelerates, the Rayleigh-Taylor instability will start to amplify those perturbations, and eventually they imprint upon the fuel and shred it to pieces. Now, I have to say that this is about 100 times worse than actually what happens in the experiment. Now, there's another problem, again associated with the Rayleigh-Taylor instability, that happens later on in the implosion. So let's imagine we've taken our 2mm capsule and we've managed to compress it 40 times in radius until it's only about 50 microns, 50 millionths of a meter across. This is the end game, essentially, where we're trying to get the fusion out at the end of the implosion. So what I have here, this is a dense region, this red bit here, and that surrounds a slightly less dense region here, which is where the plasma is starting to get hot. Now, the idea behind this is to try to make use of the fusion reactions which start in this region as a way of heating up the majority of the fuel that sits out here. So if I get a fusion reaction in the middle of the system here, it produces a helium nucleus, and that will fly out and become absorbed in the outer regions of the fuel. So that's going to heat up these outer regions of the fuel and begin the burning of those parts of the system at the same time. So this is very much lighting a match. We have a burn wave that propagates outwards from the center to the outside. We light this part of the fuel, and the burn propagates outwards and eats its way through the majority of the fuel here. So what that looks like, so this is a little bit like lifting yourself up by your bootstraps. This is why it's called bootstrap heating, of course, is we get much more energy out if we can do this. And this is central, of course, to the ignition process. This is what we mean by ignition, this self-generating heat. So what this looks like in a calculation at the end, what you've got on the right here is a slice through the density. This is the dense region here, compressing the high temperature region here. And by this time, we're generating a lot of fusion reactions in here and trying to set fire to the neighboring region. But now I want to explore what happens if, again, I don't have a perfect spherical racehorse in a vacuum. So I'm going to apply a perturbation. In this case, it's a symmetric perturbation. I uniformly distribute defects over the surface. You see, the problem I have here is if I look at this point very much in the middle, I still have perfect symmetric convergence. All of those points are still arriving simultaneously at the same time. And that's the result of putting on a perturbation which is symmetric. If, on the other hand, I just take two of those defects and don't distribute them uniformly over the surface, but put them both on this side, again, the same thing looks like it's going to happen. But at the last instant, these two collide, and they'll form a very narrow, thin jet of cold fuel, which severs the hotspot in half and makes it look like Pac-Man. So if I take that idea that I can take many, many different defects, and it's the way in which they interact together which is going to cause the most damage. So in this next calculation, I've basically used my imagination. I've put on 13,000 separate defects, all of which have different orientations, and I've basically just thrown the kitchen sink at the problem. So this is what I would call a Murphy's Law calculation. Everything that can go wrong is going wrong. And what that tends to do is produce a very different structure in the interface between the dense fuel layer and the hot part of the fuel. That has two effects. If you take cold fuel and hot fuel, mix them together, you end up with warm fuel. And warm fuel won't burn. So what we're doing is quenching the fire by pouring more cold fuel upon it, which sounds counterintuitive, but you can put out a fire if you pour petrol on fast enough. Don't try this at home. The other thing it does is it roughens up the surface, the interface between the hot region and the cold region. And that, again, will cause additional heat losses. In this case, it increases the amount of thermal conduction that loses out of the system. So the other thing we try to do is combine this effect of many, many different defects with one large perturbation. So what we've done here is take all of those 13,000 defects, but in addition, I've put a little bit too much ice on one side of my target compared to the other, and that produces another jet that severs the hotspot in half. Now, the problem we have is trying to actually understand which of these effects is happening in the experiment. All we have to look at are the X-rays or the neutrons that are emitted by the plasma. And it turns out that looking at the neutrons emitted by the plasma is an extremely powerful way of trying to work out what's happening in the very center at the core of the burn. So if you imagine that I take every single part of this calculation and turn it into one of my computational cells, there are many millions inside here, I can work out what happens in terms of the neutrons coming out of this object as it moves around inside the plasma. So as this object's moving down, it will start to emit neutrons, and the ones that come out the back will be slightly lower in energy than the ones that come out the front, simply because the ones coming out the front have the addition of the fluid velocity added to them. This essentially equates to a Doppler shift. If you like, moving a light source towards you will produce a blue shift of that light. Moving it away will produce a red shift. In this case, we have a Doppler shift of the energy of the neutrons moving around. And this can be observed experimentally. If I stick a detector down here, I'll see a different characteristic spectrum of neutrons emitted to what happens if I look up here. And this has now been observed in experiments on the NIF. Now, a lot of progress has been made in recent years in advancing towards this ignition point where we get a lot of fusion reactions and they trigger more fusion reactions in a chain reaction. But we haven't quite reached that point yet. But even if we did, the next step of turning that into an energy source is an extremely complicated and long-term path. Now, obviously, a fusion scheme such as using these very finely tuned capsules of fuel and trying to generate a pulse of energy once a second from that system is one way in which you could potentially do it. But it may not be the most cost-effective way of generating energy simply because of its complexity. So there are a number of other projects around the world that are now trying to establish whether you can achieve the same conditions of very high pressures in the fusion fuel using something that is conceptually much more simple and robust, and above all, cheaper to make. So we come back to the program at Sandia National Laboratory and the ZGenerator, which was the same system we used to look at wire arrays before. The experiments that are going on there at the moment now use a different approach. Rather than generating X-rays to try to heat the fuel, we'll directly compress the fuel using the magnetic field generated by the current. So I liken this to fusion in a beer can, for obvious reasons. But actually, the size of a target is roughly the size of a thimble. So if I take a metallic tube made of aluminium or beryllium, and I fill it with deuterium fuel, and then I pass a large current through the metal wall, and that drives rapid compression. Conceptually, this is very much simpler. I just take a thimble and implode it with a current. But of course, life's not that simple. I actually have to introduce additional things, such as a preheat laser beam that's shone into the plasma, and also a magnetic field that is added in order to try to thermally insulate the heat inside the plasma. So the name of the game here is very similar to what we had before. I have here a simulation of an imploding metal cylinder. So this is the beryllium metal, and the white region here is the surface of the fuel. You'll see that the Rayleigh-Taylor instability manifests itself again. Here it's trying to penetrate its way through into the fuel to contaminate it, but it doesn't quite manage to do that before we've compressed the fuel. And so this is the design that we have to optimize. We need to get the implosion, we need to get the thimble to be as light as possible in order to get it to implode as rapidly as possible. If we do it too thin, it's going to be too easily penetrated by the Rayleigh-Taylor instability. It will break apart as it comes in. Now, I'm very pleased to say that Sandia have been working on this very hard for the last few years, and they have recently announced that they came up with the first, what they call fully integrated shots on this system. Here is a very large magnetic field coil generating the insulating field around the thin tube of metal. Here you see some pictures of the Rayleigh-Taylor instability as the thing is imploding. Large amplitude perturbations on the outside, but the inside looks very straight and able to confine the fuel. And then finally, the X-rays that are emitted by the fuel as they finally compress are not perfectly uniform, but are actually relatively straight. So in this particular shot that was done in November, a 20 milliamp current and a 10 Tesla applied field were added with a 2 kilojoule, 2000 joule laser preheat, produced roughly 1 joule of fusion energy, which sounds like a very small amount. In fact, this was largely because they were using a pure deuterium fill, and if they'd added deuterium to tritium, that would have been 100 joules. It's still not a huge amount of energy, but coincidentally, it's almost the same amount of energy that the National Ignition Facility obtained on its first shot as well. So there's a long way to go for this system as well, but conceptually, this might be the way to make more energy. So just to close with, I'd like to say thank you to a very large number of people who over the years have contributed to some of the material that you've seen here, largely from Imperial College, but also from national laboratories in the US and also from AWE, from universities in the United States as well. But I'd like to say a special thank you to the Magpie crew, who are an extremely fun bunch of guys to work with. And it's always been very rewarding for me working with them over the years. I'd also like to say a big thank you to a very special bunch of people who have made a very significant contribution to my work. Who are these people? Well, some say that their constant obsession with giant dogs and theoretical physics and rugby act as a constant distraction to me. All I know is that I know them as my lovely wife Thea and my wonderful boys Harry and Thomas. And so finally, I'd just like to leave you with a couple of thoughts. Rather than thinking of Murphy's Law as our enemy, we should embrace it. We should try to design our experiments so that they are able and capable of overcoming all of nature's flaws that are thrown at us. Are we at last getting close? Well, in the last 6 months, Lawrence Livermore Laboratory have been able to increase the fusion yield from an imploding pellet by roughly a factor of 10 from where they were this time last year. So these are very encouraging times. We're getting into the regime where the helium nuclei that are produced by some reactions are themselves producing further reactions. So we're on the threshold of achieving this ignition process. And I firmly believe that in the next couple of years, we may hear an announcement from Lawrence Livermore Laboratory that they have indeed achieved ignition. But what does that mean? Well, what we're interested in, of course, is trying to turn this into an energy source. And by doing that, of course, we're trying to compete with the way in which energy is made at the moment. Now, the way energy is made at the moment is this. Well, it's my schematic of how it's made. It's basically a kettle. You generate electricity by spinning a steam turbine. You generate the steam for the steam turbine by heating water. And of course, the heat source for the water can be pretty much anything. Now, what we're proposing to do is to replace in this system the heat source with what equates to one of the most complicated and expensive experiments that science has ever devised. So obviously you can see that there is a very long way to go for turning something that works into turning something that's economically viable. And if we are to achieve ignition, this will be a much more significant and major hurdle. So if I ask myself, are we getting close? Well, we should be careful what we ask for. Ladies and gentlemen, thank you very much for your attention.